screen. Let's see. Oh, there we go. It's working.
Yes.
Screen sharing is working. Cool. Okay. Okay. Hi everyone. So let's see. First, before I get started, maybe there's a couple things I want to say. I have a copy of the notes for things I'll talk about today up on the wiki right now. There's a couple of errors. Well, throughout all my notes, there's going to be like little errors minus science factors of 2, though, because it's been a bit last minute. So I'm planning on going back at some point, refining it. But for now, if you want to follow along during the lecture on your own set of notes, it's on the wiki. Okay, so I'm going to start with a quick outline of what I have planned to talk about the next few lectures. So the first day I'm going to talk about late time chaos and random matrix universality. Basically, it's going to be, we're going to talk about some features we expect of chaotic systems relating to the distribution of their energy levels. And there's going to be some math having to do with random matrices that we'll use to explain that physics. And also that math will end up being useful for part 3, the third lecture. So it's sort of a bit of a dual purpose. The second day, tomorrow, we're going to talk about some signatures in gravity of these chaotic features. And then the third day, we're going to talk about very specifically one toy model of gravity, JT gravity, and how it's very closely related to some of these random matrix theory ideas we're going to talk about today. Okay, so I also have just for today's stuff, a few references if anyone wants to learn more. I particularly recommend this book here, Quantum Signatures of Chaos by Haka, if you can find that book. Okay, so now finally we'll get started on the actual stuff. The first statement I'm going to make is just that black holes are chaotic. And rather than try to give a careful definition of what it means for a quantum system to be chaotic, it's a bit tricky. What I'm going to do is show you how black holes exhibit certain signatures of chaos, some very important ones, just to give some examples. So the first and sort of simplest is thermalization. So if you have a chaotic system that's in thermal equilibrium and you perturb it, if you wait some time, any sign of that perturbation should disappear. The system should return back to equilibrium. And so how do black holes exhibit this thermalization? So we can study this by talking about the 2-point function of some field O outside the black hole, separated by some time t. So what this 2-point function is telling us is you start with the black hole in thermal equilibrium, and you drop in a particle created by O. So this particle will go towards the black hole, and eventually it'll fall into the black hole. And along the way, it might excite the black hole, and the black hole might oscillate, but these oscillations will ring down and die off, and the black hole will return to equilibrium. The particle will be inside the black hole. And some long time t later, you try to measure O again, and there's no sign that you had thrown in the particle far in the past. So this is perturbing the black hole. It eventually returns to equilibrium. So one interesting just side note is that this thermalization, this sign of it for a black hole, this ring down effect that I just mentioned, you can actually see an example of it in real life from this LIGO measurement, where they measured gravitational waves from 2 black holes colliding. And after they merge, you can hear this rapid ring down effect in the signal they measured. So that's pretty neat. And specifically, in ADS-CFT, this can be made pretty precise. In ADS-CFT, a large ADS black hole is dual in the boundary to a thermal state. And so this 2-point function of fields outside the black hole is a conventional thermal correlation function. And this was studied by Gary Horowitz and Veronica Hubenning, the organizer here. And they made a lot of this precise and talked about the rapid exponential decay to equilibrium. So that was thermalization. And another interesting signature of chaos exhibited by black holes is the butterfly effect. So what is the butterfly effect? Say you have a finely tuned state where something very finely tuned is going to happen. Say a particle appears outside the black hole at point X at time 0. The butterfly effect means that if you take that finely tuned state and you say, I go back into the past and make a perturbation before that. If you go far enough back into the past, a generic perturbation will destroy that fine tuning. So the perturbation will spread throughout the system over time. And if you go back by time TD, where TD is bigger than what's called the scrambling time, this perturbation will destroy the fine tuning. So this fine tuning event with the particle appearing at point X at time 0 will no longer happen. So this is studied by Schenker and Stanford in the black hole context, where they found this formula for the scrambling time. And in that case, there's a sort of simple picture of what this butterfly effect is describing in gravity. So here the fine tuning is that we set up a state where a blue particle W is supposed to hit the boundary. It's supposed to leave the eternal black hole and reach the boundary at time 0. However, if we go back into the past and act with V, which creates this red particle, V will fall into the black hole and meet W. And if we go far enough back into the past, they meet very close to the horizon, where this red particle will have accelerated a lot, and they'll have a large relative boost. So in that case, the gravitational pull between V and W becomes very large. And so having thrown in V will have a large effect on W. And in particular, if you go back further than the scrambling time, dropping V into the black hole, they have the effect of shifting the horizon of the black hole. The horizon will grow enough so that W gets sucked back into the black hole and no longer reaches the boundary. So this is the sense in which black holes exhibit the butterfly effect, is that perturbations thrown into the black hole will have a large effect on things which were supposed to come out at a finely tuned time. And this can be studied using this observable, the commutator squared, which measures the effect of V in the past on W at time 0. And the behavior of this function in gravity turns out to be an extreme example. This is discussed by Maldacena, Schenker, and Stanford. This observable grows exponentially with some maximal rate. And so in some sense, these black holes are maximally chaotic. So these two signatures of chaos, thermalization and the butterfly effect, for black holes, they can be seen semi-classically. But the signatures of chaos that we're going to be talking about today are actually going to be related to non-perturbative gravitational physics. So they're, for example, related to exponentially small effects in the entropy of the system. So the entropy for a black hole is 1/g², so the entropy is very large. So if something's exponentially small in the entropy, that's a very, very tiny, hard to measure effect. These effects are also related to exponentially long times. So if you take a black hole, it's in equilibrium, and you let it evolve for an extremely long time, these effects might become important. And also, these effects are related to the discreteness of the spectrum of a black hole. So Bekenstein and Hawking told us that a black hole should have an entropy proportional to the area of the horizon. So there's a number of states for a black hole that goes as e to the area. That's a finite number of states that should have some spacing between them. But in gravity, it's very difficult to see signatures of this actual finite number of states of the black hole. So these are the effects. These effects that we're going to be talking about today are some sign of this finite entropy. So the effect that the signature of chaos, or effects that I'm going to be describing today, they go under the name of random matrix universality. And I'm going to start by giving you a very rough statement of what this means. And throughout the rest of this lecture, we're going to refine it. make it more precise. So the rough statement is that the Hamiltonian for a chaotic system, in some sense, looks like a random matrix for appropriate observables. So this Hamiltonian has energy levels and it has eigenvectors. The energy levels for a chaotic system, the claim is that they are distributed like the eigenvalues of a random matrix. In particular, we're going to talk about the spacings between energy levels. The spacings between energy levels will have some statistics, and it'll share, we expect those statistics to share properties with the statistics of the spacings between eigenvalues for a random matrix. We could also can make some statements about the energy eigenstates for a chaotic system, and they should in some sense be random. This is called the eigenstate thermalization hypothesis. But we're not going to really talk about that today. We're going to focus on this, the energy levels and try to make statement one more precise. Okay, so what we're going to do is we're going to say the Hamiltonian for a chaotic system looks like a random matrix. So we're going to have to talk about what is a random matrix, how do they behave? And for simplicity, we're going to focus our attention on Hamiltonians and matrices with no symmetries, besides certain anti-unitary symmetries, which I'll talk about in a moment. It's simple to generalize to the case where you do have symmetries like translation symmetry, some charge, some continuous symmetry. But just for simplicity, we're going to talk about systems that have no symmetries besides possibly having time reversal invariance. So there's two cases if a system has time reversal invariance. The time reversal operator T can square to 1 or it can square to -1. And as a side note, in the SUSY case, there's more symmetries, but we're not going to talk about those for simplicity. So for the class of Hamiltonians or matrices that are Hermitian, we're going to separate them into three symmetry classes. There's the Hamiltonians with no time reversal invariance. There's Hamiltonians with time reversal invariance where t squared is +1, and Hamiltonians with time reversal invariance with t squared -1. And the structure of these Hamiltonians, and therefore the statistics of their eigenvalues, are going to be different for each of these three cases. So we have to talk about them separately. And really, we're actually going to focus on the case with no time reversal invariance because it's the most simple. And so here I have an example of sort of what's the structure of a matrix from each class. If you don't have time reversal symmetry, Hamiltonian is just some Hermitian matrix, and it can have distinct eigenvalues. And here I've written Hamiltonian so that it has L eigenvalues. So we're going to work in an L-dimensional Hilbert space. Throughout this lecture, we're going to use L to talk about the dimension of the Hilbert space. So if you do have time reversal invariance and t squared is +1, the Hamiltonian is real symmetric, and you can bring it to this block diagonal form if the eigenvalues are degenerate. And if t squared is -1, it's a little bit more complicated. The blocks are real quaternions. And these three classes, sometimes referred to as Dyson's threefold way. So because these two cases are, we have these degeneracies we have to worry about, they're a little bit more complicated to deal with. We're going to really focus most on this first class, just a general Hermitian matrix with distinct eigenvalues, no time reversal invariance.
Question?
Mm-hmm.
Could you go back to the previous page for a second?
Yeah.
Why are you saying that the second class is real symmetric? That doesn't look real symmetric to me.
Oh, it's real symmetric in so if you can always bring a real symmetric matrix to this form by a unitary transformation, but by an orthogonal transformation, which is more natural, it won't be turned into this.
I see. Okay.
Does that answer your question?
Yeah, thanks.
Okay, so what I've just told you about is three classes of Hamiltonians that we'll consider. But we want to talk about random matrices. And to talk about the random matrices, we have to give the set of matrices some ensemble, so we have to give the ensemble of matrices a distribution. We're going to call that distribution P of H, so that the probability of finding matrix H is P of H, or probability of finding matrix H is P of H. And our goal for today is going to be, for certain P of H's, what are the statistics of the energy levels of H in that ensemble? And of course, the statistics of the energy levels depends on our choice of P of H. But what we're going to see is that there's some certain universal features that are robust, that don't depend very much on our specific choice of P. To illustrate these features, though, it's useful to pick a specific choice of P of H, and then we'll see sort of how these things are universal and independent of P of H. And the specific choice of P of H that we're going to focus on, it goes under the name of GUE for the no time reversal symmetry class, GOE for the time reversal squared +1, and GSE for time reversal squared -1. So now we're going to describe what exactly are these distributions for these different classes. So the one we're going to really care about is the Gaussian unitary ensemble. So it's the ensemble of Hermitian matrices, no T symmetry, where this probability distribution I've written right here. But first, we're going to talk about a specific feature of this, which is that this distribution P of H is invariant under conjugating H by a unitary matrix. So what this means is that this distribution only depends on the energy levels of the matrix. Furthermore, we're going to choose a specific choice of P, which is this function here. It's e to the minus L over 2, where L again is the size of the matrix, times trace H squared. And dH, we're going to integrate over each element of H separately with this flat measure here. So if we look at this trace H squared, we can recognize it as a sum over Hij squared. And so this is telling us that each element of H, so each Hij, is independently Gaussian distributed. So this is sort of the simplest measure you can think of for a matrix, which is that you take each element of H and you say this is a Gaussian. Well, some of them are real, some of them are complex, and we'll take the real and imaginary parts and say each one is just a random Gaussian number with some variance, which is 1 over L. And then, as a side comment, this sort of ensemble is easy to generalize by taking this trace H squared to be trace V of H for some function V. If you do this, the distribution still has this property that it's unitarily invariant. And this is going to be more, this is a bit of a side point. It's more important in the third lecture, though. Okay, so then I have a couple of slides about the other symmetry classes, but we're not going to talk about this very much. So I'll skip this for now. So our goal for now is to say, what are the statistics of the energy levels in this Gaussian unitary ensemble? We've given a probability distribution for the matrices, but what is the probability distribution for the eigenvalues themselves? So the matrix elements are independent random numbers, but the eigenvalues themselves will not be independent random numbers. So understanding that distribution is our goal for now. So the way we'll do this is we'll express our matrices H as diagonal matrices conjugated by some unitaries. And then we'll write this probability distribution for H as a probability distribution for the energies in this unitary matrix. So we basically have to take this Gaussian distribution we saw, and when we change variables, we need to find the Jacobian. So we're going to go into this in a little bit of detail, but I'm going to leave some of the detail for aside for, and you can look at these notes if you want to know more. But here's the rough idea. So the first thing that we're going to do is take this P of H and express it in terms of the eigenvalues and these unitaries. Now, because we've chosen this P of H to be unitarily invariant, it only depends on the eigenvalues, not on the unitaries. So that's nice and simple. So this P of H in terms of the eigenvalues is this nice set of Gaussians. The trickier part is dealing with this measure factor DH and finding this Jacobian when we change variables. So the way we're going to think about it is we're going to think of the HIJs, these matrix elements, as coordinates in the space of matrices with some metric. And then the measure is square root of the determinant, the metric, times the product of D over D, the coordinates. So here's an expression for this metric. It's the flat metric. Right, is trace DH. So when we change variables to the energy eigenvalues and the unitaries, what we can do is look for the metric in those variables or those coordinates. And then the Jacobian is just the square root of the determinant of that metric. So I'm not going to go through this. This is just some algebra working out the metric. So you take H, you express it like in terms of the unitaries and the eigenvalues, and you study DH, and then the metric is trace DH squared, and you work it out and simplify. If anyone's interested, there's it's sort of a neat procedure of working that out. But for now, I'm just going to focus on the result. So the result is that this Jacobian is this function here. It's a product over pairs of energies of this energy difference squared. So you have this Jacobian. Oh, you also have some measure for the unitaries, which I'm not going to go into detail right now because we're not interested in the unitaries. It turns out to be what's called the Haar measure on the unitary group. It's the natural measure for unitary matrices. So this thing here, this Jacobian is going to be very important for us. So ignoring the part of the measure over the unitary matrices, focusing on the eigenvalues, we find this measure here, and we're going to call this thing here the Vandermonde determinant squared. So the Vandermonde determinant is this product over energy pairs of the energy differences, and here we're just squaring it. And as a homework problem, if anyone's interested, if you work out this procedure that I skipped over in the last couple of slides for the GOE or GSE cases, you find the same sort of measure for the eigenvalues, except with different powers of the Vandermonde. For the GOE, which is the real symmetric matrices, time with the time reversal invariance squaring to +1, you find 1 power of Vandermonde. For the other symmetry class, where t squared is -1, you find a 4th power of the Vandermonde. And so I'm saying this because it's actually somewhat important that this Vandermonde shows up in this measure in all these different symmetry classes. The Vandermonde is the important thing. The specific power the Vandermonde shows up to is the main difference in the statistics of the eigenvalues for these different symmetry classes. Okay, so let's look at this measure, this Vandermonde squared measure factor. And we can see that one interesting feature is that coincident energies have probability 0. So it's you have 0 probability of having degeneracies in this ensemble. And so you can think about this, it's roughly like the origin in polar coordinates has 0 measure. The physically important part of this is that eigenvalues in for these random matrices are very unlikely to be very close by. So the probability for having a small energy difference, EI minus EJ for nearby energies, the probability goes as the square of that difference. And this is goes in the name of eigenvalue repulsion, because in this measure tells us that nearby eigenvalues have like a sort of repulsive force making them unlikely to be very close by. Now, this fact, this eigenvalue repulsion, is really going to run the show when it comes to discussing the statistics of the energy levels. And it's basically because this Vandermonde, this Vandermonde appeared as coming from the measure factor of dH. It didn't come from this probability distribution of H. So the appearance of the Vandermonde in these random matrix ensembles is independent of your choice of P of H. We've chosen a specific Gaussian one for simplicity, but the Vandermonde is always going to be there. And this eigenvalue repulsion is always going to dominate the nearby energy level statistics. So no matter what random matrix potential or random matrix distribution you choose, you'll always have this fact that nearby eigenvalues have small probability of being very close. And in fact, this is going to turn out to be to give us some very quantitative universal behavior. So this eigenvalue repulsion, as I've described it, somewhat a qualitative picture, but we're going to find very quantitative statements to make. The first example of that is we're going to say, given a random matrix from this GUE symmetry class, what is the distribution of the nearest neighbor spacings? So E1 minus E2, E2 minus E3, E3 minus E4. What is the probability of any one of those having being of size S? So in general, it's actually very difficult to find that distribution. So we're going to start with just a simple example. We're going to take a 2 by 2 matrix, so L equals 2. So this 2 by 2 matrix has eigenvalues E1 and E2, and we're going to study the difference S between E1 and E2. And we've labeled the sum of the energies as E tilde. So to understand the distribution of S, we can take our distribution for E1 and E2 and integrate out the total energy, just leaving a distribution for the difference. And so basically, because this P of H is a Gaussian, it's very simple. So it's a Gaussian in S and it's a Gaussian in E. So integrating out the total energy E is easy. It's just a Gaussian integral, and you're left with this distribution for S, the energy difference. So here the S squared comes from this Vandermonde square, E1 minus E2 squared. And you also have this Gaussian part from this P of H. So let's look at this. Let's plot this probability. So this is telling us that for this 2 by 2 matrix, you have vanishing probability to have the two eigenvalues be the same. It vanishes like S squared. Most likely, they'll be spaced this far apart. And they have a distribution that goes like a Gaussian in S for these larger spacings. So this was pretty simple to do for a 2 by 2 matrix. But the remarkable thing is that this same distribution turns out to be a pretty decent approximation, even for a large matrix. So for like a 200 million by 200 million matrix, the distribution of these nearest neighbor energy spacings follows the same shape, same quantitative shape, in fact. It's a rough approximation. I think I remember it's something like a 1% approximation. So it's not parametrically good, but it's a decent approximation, even for these large matrices. And briefly, I'll say that if we had, instead of, so what we had started out by saying is you take a matrix H and give it a probability, which is basically saying that the energy level, the matrix elements are independently distributed. As a result, the energy levels were not independently distributed. If you would instead said, let's take an ensemble of matrices where the eigenvalues are independently Gaussian distributed, you'd find a very different form of this nearest neighbor distribution. You'd find what's called a Poisson distribution. So if you're taking the eigenvalues and making them independent, you're just like throwing darts at a board independently. or darts on a line, you'd find that the spacings between the darts follow this Poisson distribution, which I've drawn in purple here. So there's very, very different. You can see these two very different shapes. And this purple thing, the Poisson distribution, is the statistics of energy spacings that you'd expect to find for an integrable system. So just looking at this distribution of energy levels will tell you whether your system is chaotic or not. If it's chaotic, it should follow this shape. If it's not chaotic, it will follow this shape. And this shape here in black, yeah.
Sorry, here, is it clear that like, where is the chaos coming from here?
Oh, sorry. This is, I'm basically telling you I'm just telling you a statement that without explaining it, which is that this function here, which is the distribution of eigenvalues for a random matrix,
Yes.
is also what you expect to find for a chaotic system.
But
So
you're gonna show us
why.
this. Okay.
Yeah. So it's so we'll talk more about that. But for just an example, this how was this shape found? This s squared e to the minus s squared. This is called the Wigner surmise, because Wigner was studying the spacings of energy levels in a heavy nucleus, and they had measured these spacings, and so he just wrote down this function. He surmised this function, guessed it, and then he found that I'm not sure if it was him and Dyson found that that same shape that he had guessed to describe the statistics of the nuclei energy level spacings is also appearing in this random matrix theory context. So in that case, this is how it was discovered historically. It was this is so basically the first connection people had seen between these random matrix level statistics and statistics for an actual chaotic system. So the fact that these chaotic systems, like these heavy nuclei, or we expect black holes, also have this same statistics of these nearest neighbor spacings, is basically what I mean by this random matrix universality. Universally among chaotic quantum systems, any chaotic quantum system will have these nearest neighbor energy spacings following this Wigner surmise, no matter what else is true about the chaotic system. It could be in 1 dimension, 3 dimensions, it could be electrons, it could be whatever. It could have any sort of particles, as long as it's chaotic. It'll have this quantitative shape, this Wigner surmise. So this is so the universality here is saying that it's independent of basically any fact about the system except for that it's chaotic. And so this is a statement I'm making that has evidence for it. There's a lot of experimental numerical evidence where people have studied these spacings in given systems and found this Wigner surmise. There's not a general understanding of why this is true. So it's just a fact that has been noticed. And in some cases, there's some theoretical understanding of why that's true. And essentially our goal will be to get a theoretical understanding of why this is true for black holes specifically. So before we get on to black holes, we're going to talk a lot more about this random matrix universality, because this there's an even stronger statement than the statement I just told you about the nearest neighbor energy spacings in the Wigner surmise. Actually, sorry. Before that, there's one point I want to make. So it's sort of weird what I'm saying. I'm saying that a chaotic system like a black hole or a hot gas of particles or something like that should have these random matrix statistics in the energy eigenvalues. For those cases, we're not studying a genuine random matrix. Like the Hamiltonian for gas of particles is the Hamiltonian for gas of particles, not a randomly drawn matrix. So why might you expect these random matrices to have much to do with those specific non-random systems? So the rough idea is that by studying these random matrices, what we're seeing is that matrix has to be very fine-tuned so that if you want these energy levels to be nearby. So generic matrices will have this eigenvalue repulsion. Their eigenvalues will not be too close. So this statement about the random matrix universality is basically telling us that chaotic systems are generic in that sense. The Hamiltonian of a chaotic system is not finely tuned. So it's not random, but it's not finely tuned so that the eigenvalues have this nearby almost degeneracies.
I have a question.
Mhm.
So how universal is the Gaussian tail?
The Gaussian tail, that I actually don't know very much. So in the case we just looked at, it seemed to follow from our specific choice of this Gaussian unitary ensemble. I think I'm actually not sure in this case. We're going to talk about a better sort of quantity in a moment, where we will be able to say more about how universal it is. So maybe I'll get back to that point in a bit. So basically, what we just talked about is the distribution of nearest neighbor spacings. The thing which is actually a little easier to study and make statements about is the distribution of energy differences, not just between nearest neighbors. So we can describe this distribution as P of E bar and delta E. That's saying if you have energy levels E and E prime, this thing is the probability of having them spaced by delta E with their average energy being E bar. So in this Gaussian unitary ensemble, we'll be able to find, well, we'll make some statements about how to find this this function in the GUE, and I've plotted it below. The dependence on the average energy is not so interesting. So we're going to focus on the dependence on this energy difference. So what we're seeing is this red curve. This is this function P of delta E. For nearby energies, it vanishes like delta E squared. So this is that eigenvalue repulsion we just saw. There's a little peak at some energy spacing, which is like goes as 1 over L. This is telling us that you're sort of likely to have, if you have an energy at E, you're sort of likely to have an energy at E plus delta E, where delta E is 1 over L. You're also likely to have another one at 2 over L away and 3 over L away. So there's these peaks which are evenly spaced. So this distribution that we'll find, this red shape, is saying that a typical matrix in the GUE has like roughly evenly spaced energy eigenvalues. There's also a sort of an overall shape. If you sort of average out the oscillations, you find this black dotted line. So it's like minus 1 over delta E squared. This is going to, we can think about this as some sort of long-ranged anti-correlation between eigenvalues. If you have an energy at E, you're unlikely to have other eigenvalues too close. So this is the picture we're going to try to understand in the GUE, and we're going to now talk about how you can derive this. So yeah, and before we do that, I'll say now that the stronger statement of random matrix universality is not just that this Wigner surmise describes a chaotic system, but that this function in red also describes any chaotic system. The same function in red. We'll write down, in fact, a precise formula for that function in red. And we think that it should hold in a chaotic system up to some large energy spacing delta E, which is called the Thouless energy. So the Thouless energy depends on the precise system, but for any chaotic system, for sufficiently small delta E, we're going to say that we expect this behavior for the statistics of its energy spacings. So this is the stronger version of random matrix universality, and this statement is not going to depend much on this choice of distribution for the matrices. So it's somewhat it's very universal in that sense. So what we're going to do now is go through a little bit of the math of how to derive that function. So I don't want to get into too much detail. So I'll have a lot of this math left over in these notes if you want to go back and look at it afterwards. But for now, I'm just going to go through the main points. So the thing we're going to do is we're going to define this density of states rho of E. It's a sum of delta functions at the locations of each eigenvalue EI of a matrix H. And we often like to think about the normalized density where we divide by L. This is like a normalized probability finding an energy at E. So the thing we're interested in is averaging these probabilities, rho tildes of E, over the ensemble of matrices H. So we're averaging over H, that's averaging over the energies in these delta functions. As a result, we'll get a smooth function, the average rho, which is like the probability in the ensemble of finding an energy at E. So the thing which is related to this random matrix universality is the pair correlation function, which is the average of rho at E, rho of E prime. So this is saying if you have an energy at E, what's the probability of having an energy at E prime? And for E and E prime sufficiently far separated, you can think about the probability for having energy E and E prime is basically independent. But for E and E prime nearby, this eigenvalue repulsion and all that stuff will become important and give us a very important behavior of this function. So some of this math of how to derive it is going to be pretty useful in a later lecture. So I'll go through it a little bit now. As an example, we're just going to first say, how do we calculate the average of rho tilde of E? So I've given the E label a hat, to say this is the external energy and the observable, to differentiate it from the E's we're integrating over when we average over the H's. So here, average of rho is an integral over H, P of H rho, and then I've changed variables to the energies and the unitaries and integrated out the unitaries. So we're left with the integral dE, the Vandermonde measure factor, and this Gaussian probability for each E. So what we like to do is combine these things into an effective action for the eigenvalues. So we'll pull out a factor of L squared out front, and we'll see why in a moment. So this effective action, there's this Gaussian term from here, and there's also this term which is from the Vandermonde. So this
We're
is
not
like
interested in U at all. Are we not
Pardon?
caring about U at all, or
We're not caring about you. So it's because rho doesn't depend on you. So it can be, you can be completely integrated out. It's just a normalization factor.
right? Okay, yeah, thanks.
Mm-hmm. So the Vandermonde in this effective potential contributes like a pairwise repulsive, logarithmic repulsive potential between each eigenvalue. And just very briefly, you can notice that we have a sum over L terms here divided by L. So this is like of order 1 in L. This is sum over L squared terms divided by L squared. So this is order 1 in L. So altogether, the effective action scales like L to the 0. And we have this factor of L squared up front. That's going to be important in a moment. So what's the physical picture of this effective action? We can think of each energy as like a particle in a potential well. So here we have a Gaussian potential well. And each particle has a repulsive force with the other eigenvalues. And this is often called the Coulomb gas or fluid technique due to Dyson. The Coulomb is because this log potential from the Vandermonde is like the Coulomb potential in 1D. So this is like having a bunch of charged particles on a line with a potential well. So here the potential well is Gaussian, but we can imagine changing the potential well. And you still have this repulsive Coulomb force from the Vandermonde. So our goal is then to say, what's the sort of classical saddle point configuration of all these particles in this potential well? So if we find the saddle point location of all these particles, that'll tell us the density of states, this rho that we're looking for. And to do that, it's useful to introduce a quantity called the resolvent. Right now, the resolvent is, we're not going to make that much use of it. I'm introducing it now because it'll be pretty key in a later lecture. The idea of the resolvent is just that it has poles at the location of every energy. So here we've written resolvent for a fixed matrix H with energies EI, and we're going to talk about averaging the resolvent maybe. But for a fixed matrix, it has poles at the locations of the energies, and then we can write it in terms of this rho of E as an integral with rho of E like this. So because of these poles, we can extract this rho of E, which is the delta function at each energy, by taking the discontinuity of the resolvent across the real axis. Or here we use this formula that the 1 over E plus I epsilon is like a principal parts plus a delta function. So the strategy of this Coulomb gas method is to, you take this effective potential and you vary with respect to EI to find an equation of motion for E. Basically, this is saying that the equation of motion is saying that E has zero force when you add the force from the potential, from the repulsion from all the other eigenvalues, plus the force from the potential well. So we want to demand that each eigenvalue is stationary. There's no force acting on it. We get this equation, and this equation isn't very useful by itself. It's an equation for a given EI. The trick that's useful is to multiply this thing by something which is E hat minus EI, and sum over EI. Now we get an equation relating two functions of E hat, and if you are interested, you can try rearranging this and find this equation here in terms of the resolvent of E hat. So the equation that we find resulting from the equations of motion for this, it's like a quadratic equation for the resolvent, plus a term which is like R prime divided by L. But L, we're going to take to be very large. We're taking the number of eigenvalues, the size of the matrix to be very, very large. Then we expect that this term is small and can be ignored. That means we're left with just a nice, simple quadratic equation for the resolvent. And we can solve for the resolvent, and we find this thing here. Okay, so this is the saddle point value for the resolvent. From that, we can extract the density of states. A moment ago, I told you that the resolvent for a fixed matrix is a sum of poles, the location of each energy. So basically what's happening is that when you average over the matrices, all the poles get smeared out into a branch cut, a branch cut that lives where the energy eigenvalues are. So here, the branch cut lives from energy equals minus root 2 to root 2. And so we find this density that's non-zero in this region here, and it's given by this semicircle formula. It's called the Wigner semicircle. So this is this smearing out of the poles into a branch cut is a pretty generic feature in these random matrix integrals, and it's going to be somewhat important in the third lecture. So that's why I'm mentioning it now. So let's take stock of what we've done so far. We've tried to study these this density of states, rho tilde of E, averaged over the random matrix ensemble. And we found the average density, and it takes this semicircle shape. But this semicircle shape depended crucially on this specific choice of potential. So if we take this potential to be pretty different, maybe it's got a few bumps in it or whatever, we'd expect that the average density of states looks pretty different. It will reflect the details of potential. So this shape here, the semicircle, is not universal. What turned out to be universal is the behavior of the fluctuations around the saddle point. So that's going to be the thing that tells us about this eigenvalue repulsion. So let's take this action here, and a useful trick is to rewrite this action by replacing the sums over energies as integrals weighted by the density of states rho tilde. So we have two factors of rho here in this repulsive term, and one factor of rho in this quadratic potential term. And we're trying to do the integral by saddle point. And so what we'd like to do is express rho as the saddle point value plus small fluctuations. And we want to study the quadratic term in the small fluctuations. So here, this is linear. It doesn't depend on, so there's no quadratic term that depends on this piece here. So that's a hint of this universality, which is that if we had replaced the quadratic potential for the eigenvalues by some other shape, the Gaussian fluctuations in the density don't care about it. Instead, they only care about this Vandermonde logarithm term. So we find this quadratic term for the fluctuations, and it depends. This thing depends on e minus e prime, so it's natural to go to Fourier space and diagonalize it. Here, S is a Fourier variable. So in Fourier space, this is an expression for the quadratic piece of the effective action. Okay, so we're going to use this to study the fluctuations of the density around this average semicircle value. So to do that, we're going to calculate correlation functions of rho of E. So the average density, the thing that's not particularly universal, is just given to leading order by this semicircle value. And then there's small fluctuations around this semicircle. The thing that we're going to be more interested in is this pair correlation function, the correlation of the density at E and E prime. So if we try to calculate this thing and do the integral by saddle point, to leading order, we find a contribution where we replace each row with its saddle point value. But then we also have a contribution from a propagator between the two rows. And here I've written it in Fourier space with S and S prime. And then if we use this result we found for this propagator, we find this contribution to the pair correlation function, rho rho. So this contribution is minus 1 over L squared times 1 over the energy difference squared. So notice that here it's suppressed by L squared. So it's the fluctuation around the saddle point value is small, and that's basically because this the effective action had an explicit factor of L squared out front of it. So what we did is we did this perturbative calculation in 1 over L. We had a saddle point and we studied the small fluctuations. There can also be non-perturbative effects, which are not going to be able to see by doing this expansion around the saddle point. And those are actually sometimes important. And here I'm going to write the full formula because it's actually important and interesting. That includes all the non-perturbative effects. So I'm not going to be able to derive this when I don't have enough time for this, but this is the exact formula for this pair correlation function in the GUE. So it's a sum of two terms. Here's 1 over minus 1 over L squared times sine squared of L times the energy difference divided by the energy difference squared, plus 1 over L times a delta function E prime. So this term is pretty simple. This is saying that if you have an energy at E, you also definitely have an energy at E prime, because E prime equals E. So this is just saying that this is coincident energy delta function. This term is more interesting. So the sine squared oscillates very rapidly in the energy difference because L is very large. This thing also decays as 1 over the energy difference squared. It's useful to take sine squared and write it as 1 minus cosine. And then this term becomes a sum of two terms. One is precisely this thing that we just saw from the quadratic fluctuations around the saddle point. It's perturbative in 1 over L. And then there's a non-perturbative piece that has its cosine. I'm saying it's non-perturbative because cosine is like e to the I times a number times L. So this is like not e to the 1 over L. So this function here called a sine kernel, it has this average piece, if you average out over the oscillations, which is sort of easy to see. It's this perturbative thing, and it also has a non-perturbative piece. So
how does one derive it? Like just as a not in detail, but can you just like indicate how one derives it?
yeah, so there's a few methods. Maybe we'll have probably we won't have time on Wednesday, but one method is if you, let me go back to this. If you can write this integral, you can write this thing here in terms of a bunch of harmonic oscillator wave functions. So the Vandermonde times this Gaussian, you can write as some, you write in terms of like Hermite polynomials or harmonic oscillator wave functions. And then using like the WKB expansion of those harmonic oscillator wave functions, there's a way to sort of turn this integral into something that is a simple function of the harmonic oscillator wave functions, which then the WKB approximation of those will know about these rapid oscillations from this cosine. So that's maybe
Okay.
yeah.
Okay, thanks. Yeah.
And in some of the references I put at the beginning of these slides, they'll talk about all of that if you're interested. So this function, this sine kernel function that I've shown you, we can think about it as this pair correlation function by changing variables to like an average energy and energy differences. And I'm going to plot this again. I plotted it before. Here we can see that this there's this long-ranged anti-correlation in black, which is that perturbative piece. And then on top of that, there's these red oscillations from the non-perturbative piece. So the non-perturbative piece, it knows about the short distance behavior. It's not singular at short energy. It knows about that eigenvalue repulsion. It also knows about this discrete spacing. The perturbative piece sort of knows about a coarse-grained feature of this function. So it's a lot easier to see, and it's going to turn out to be. So what we're going to talk about in a second is a way to sort of separate the perturbative and the non-perturbative piece in a sort of natural observable that sort of depends more simply on this perturbative part. But sorry, I'm getting a little bit distracted. Yeah. So what we've done so far is I've said this function here is this pair correlation function in the GUE. It tells you the statistics of the energy differences in the GUE. And it's a precise shape, and it's given by this sine kernel formula. So the statement of the random matrix universality is that any chaotic system with many energy levels obeys the sine kernel behavior to a good approximation, up to some large delta E called the Thales energy, which is non-universal. So what this is saying is, like, if you take a chaotic system and you manage to find its energy levels somehow numerically or something like that, and you plot a histogram of them, you plot a histogram of the spacings, you should see the sine kernel shape emerging quantitatively. It's not just this feature of the eigenvalue repulsion and peaks, it's the exact sine kernel shape should be what you find. So that's a pretty strong statement. This statement is known as the Bohigas, Giannani, and Schmidt conjecture, BGS. And there's a decent amount of evidence for it. There's not a general understanding. but there's a decent amount of evidence and there's some amount of theoretical understanding in specific systems. So people have studied some simple systems numerically. They plot the energy levels, they find this sine kernel. They've studied something like chaotic billiards. If you have a funny shaped billiards table and the quantum billiards on that table, you can study that and you find the same behavior. The SYK model, numerical studies have shown this, and there's some theoretical understanding. And there's, in some more general systems, there's something called a nonlinear sigma model approach. It's very different than what I've talked about, which gives a little bit of a theoretical understanding of sort of why you expect this average sine kernel behavior for an actual fixed, non-random chaotic system. So this is the random matrix universality, which should apply to any chaotic system, regardless of dimension or regardless of what matter it has, whatever. It's very, very generic feature we expect of chaotic systems. In particular, we think that it should apply to black holes because black holes are chaotic. So in the remainder of like next lecture and the lecture after, that's going to be one of the questions we're going to try to address is, in gravity, can we derive this sine kernel formula, basically? So that's a hard problem, and in the next couple of lectures, we're only going to look at some simple cases where we can say some things. But I just want to emphasize that this is a feature that we really do expect to be true for like ADS CFT with the n=4 super Yang mills on the boundary. Is a statement we expect for that. And so somehow if you manage to plot the energy levels for that system, you should find this behavior. So we need some sort of explanation for that in the gravity dual. So here on this page, I have this picture here. Maybe should have put this in here earlier, but I put it in the last minute. This is an example of the energy spacings for a chaotic system with these random matrix statistics. Specifically, this is the energy levels for the SYK model, which is related to black holes, simple black holes. So we can see some of these features that we're talking about. None of the energies are too close to each other. They're sort of roughly evenly spaced. So go back to this, the energies, these little peaks, they're sort of shallow. So the eigenvalues have some room to move around, but they're roughly evenly spaced and they're definitely not too close. So this sort of picture is a thing you should see if you diagonalize the Hamiltonian of n=4 super Yang mills. So I think I have maybe a little bit of time left.
You have about 5 minutes.
Okay, so I'm gonna try to end. Yeah, good. I have hopefully 5 minutes left.
Oh, sorry.
Left to say.
You have 10 minutes. 10 minutes.
10 minutes. Okay. Cool. So if we want to try to study this problem in gravity, like where's the sine kernel? Well, the straightforward thing to do would be to say, let's just diagonalize the Hamiltonian for a gravity system. But that's pretty hard to do, especially in gravity. In many ways, the path integral is a little bit an easier tool. So we want to find something that's a little bit easier to study using the path integral. So instead, we're going to focus on a different quantity than this pair correlation function. It's very closely related to the pair correlation function, but it's going to be more natural in gravity, a little bit easier to study. So this quantity is called the spectral form factor. So I'm going to briefly describe it. It's the last thing I'm going to talk about. So the spectral form factor, it's you take the partition function, thermal partition function z of beta, continue to beta plus it, and then take the modulus squared. So if I write out the partition function as a sum over energy eigenvalues, I have a sum over pairs of energy, EI and EJ. I have this Boltzmann weight piece, and then I have a sum of these phases, where the phase is T times the energy difference. And then we can furthermore write this discrete sum over energies as an integral over energies weighted by these densities of states. So we can see here, it looks like if you change variables from E and E prime to energy sum and energy differences, this part looks like a Fourier transform with respect to the energy differences. So basically, we can see that if you take the spectral form factor, the function of beta and t, and you do basically inverse Fourier transforms, you'll find the product of energies. So this spectral form factor is like a Fourier transform and a Laplace transform of the pair correlation function that we talked about earlier. So, for example, if we try to calculate the average spectral form factor in the GUE, we just take this average of the densities and use our sine kernel formula. So, sine kernel formula has says rho rho as this factorized semicircle piece, and has the sine squared part and has the delta function. And like I said, it's like a Fourier transform in E minus E prime. The integral over the average energy, E plus E prime, it's non-trivial for this piece, but here, these two terms don't really depend on the average energy. There's corrections where this is only accurate for sort of average energies near the center of the semicircle. If you move away from the center, there's dependence on the energy sum, but it's sort of weak. We don't really care about it. So we can roughly think of the spectral form factor as a piece from these two terms plus the Fourier transform of these guys. So let's think about those separately, these terms and these terms. So the contribution of these guys, these are these semicircle formulas for rho naught. Fourier transforming the semicircle, it's a smooth function, semicircle. So the Fourier transform of a smooth function decays. And here, when I plotted it, I'm calling the piece that comes from these two the slope. So it's a decaying function of t. For t equals 0, let's go back up and remember that our spectral form factor is just z of beta squared t equals 0. Z of beta is the thermal partition function. It goes like the number of eigenvalues of the entropy, e to the entropy, which is L, and we're taking it squared. So at t equals 0, the spectral form factor starts at size of L squared, and the smoothness of these functions causes the spectral form factor to decay. Eventually, contributions from these guys take over. If you work at the Fourier transform of this stuff, you find what's called the ramp and the plateau. So there's a linearly growing piece that's like, I should have written it actually. The ramp is like t over, I think it's 4 pi beta. So it's exponentially small compared to this slope piece. The slope piece is proportional to L squared, but decays. This is proportional to L to the 0, but grows in time. So it grows linearly for a time up to time of order L. So it grows for a very, very long time, if L is large, and then it stops growing and becomes this plateau here. So let's dissect each of these terms a little bit more. So the slope, as I just said, comes from this rho naught piece, the semicircle. The ramp we can think of as coming from the perturbative part of the sine kernel, where we average out the oscillations. The reason is that these oscillations are very fast. It oscillates like e to the I energy spacing times L. So the Fourier transform is only sensitive to these oscillations if t is of order L. So for t less than L, it turns out that the Fourier transform, the spectral form factor, it doesn't see the oscillations in the spectral form in the sine kernel. So this part is the simple perturbative part of the sine kernel, gives this ramp, and at these long times of order L, it suddenly transitions to this plateau, which this sudden transition is due to these rapid oscillations. And then lastly, this delta function is just basically sets the overall height of this function. It's not very interesting. So again, just because these things are important, I'm going to reemphasize slope comes from this continuous density of states. It decays. The continuous density of states leads to decay. The ramp and plateau don't decay. So that's because they're sort of related to knowing about the fact that rho is not quite continuous. It has discrete spectrum. So the ramp and the plateau remember that for each element H of the ensemble, there's a discrete spectrum. So for this reason, these ramp and the plateaus are interesting probes of the discreteness of the spectrum of the underlying matrices in this random ensemble. And so in the black hole context, what we're going to do tomorrow is we're going to say, how do we calculate the spectral form factor? And can we see some signature of this ramp and plateau? That will hopefully tell us something about signatures of the underlying discrete spectrum of a black hole. Okay, so that's it for now. Yeah,
Thank you.
okay.
All right. Questions for Phil?
I have a question.
Mhm.
So earlier I asked you about the universality of the Gaussian decaying tail
Mhm.
of the Wigner surmise. I'm not sure if you answered that.
Oh, yeah, sorry, let me, so my answer for the Wigner surmise is I'm not sure. But I can give you I can answer a related question, which is the large delta E behavior of this sine kernel. So the Wigner surmise is sort of the small delta E part of this that only applies for nearest neighbor energies. This is sort of like the generalization to more than nearest neighbor energies. And so we can ask, is the tail in this sine kernel, is that universal? And the answer is yes to that question. But for the Wigner surmise, I'm not sure.
Okay, thank you.
Other questions? Okay, so I guess it's a good time to stop the recording. And